Hello everyone. In this session, I'm going to look at one of the most important algorithms for classification of the data. So classification comes under the supervised learning process. We have discussed earlier that supervised learning has two major objectives. One is a classification where I'm trying to predict the group or the class based on a set of variables, or I am also having another major objective which is a numerical prediction. So this session I am focusing on the classification predictive learning predictive modeling algorithm. So one of there are so many algorithms that are associated with classification, but in this context I would be using the nearest neighbors analysis. So we will be talking about different kinds of algorithms as a part of this sessions, as a part of this course on machine learning. But in this session, one of that major algorithms that I'm going to look at is the nearest neighbor algorithm. So we'll see how to use it. What is the way this nearest neighbors algorithm tries to learn from the data, and how does this algorithm help me in doing the classification of the new data that I am supplying to it, right? So from the existing data, how will this algorithm learn, and when I am giving a new data to it, how will it produce the results for the new data? So that is what is our objective here. So we would be initially understanding what is this nearest neighbors algorithm all about. So we need to understand how do we really do the classification of the data using this nearest neighbors. We'll have a detailed discussion of the algorithm per se, KNN, which talks about k nearest neighbors. So if I am talking about 1NN, it means one nearest neighbor, two nearest neighbors. So in general, we are calling it as a KNN algorithm, which is the k nearest neighbors algorithm. So how do what do I mean by near? How do I calculate how near are the various data points? So that is where we have to talk about the distance computation. So we need to understand what is the mechanism that is available to compute the distance. So we have to talk about that aspect. Now, what is an appropriate k to choose? Should I choose 1, 2, 3, 10, n? So what is an appropriate k as a part of that KNN algorithm? How should I really plan myself to choose an appropriate value for k? And then now looking at, I have a data, what are the various initial settings I need to do to that data so that I can comfortably execute a KNN algorithm on that data. Now, just as an offbeat here, generally this KNN algorithm is called as a lazy learning algorithm. Right? We will have to see why it is typically called, but otherwise the KNN algorithm is slightly different from many other algorithms that we see in the machine learning world, where because of which it is called as a lazy learning algorithm. So we need to understand why people call it as a lazy learning algorithm. And finally, once we get a basic hold of the conceptual aspects of this entire nearest neighbors algorithm, we'll take a data set, we will try to classify the data we will try to come out with a classification model and use that classification model for computing the predicted class for a completely different set of data. So that is what is our overall objective of this session. So we would be using R extensively here. We would be using the KNN algorithm also to do this entire classification process. Now, the major logic or concept behind this nearest neighbor algorithm is things that are alike, right? We are talking about 5 people, 1, 2, 3, 4, 5. So let's say if these 2 people are more or less alike, then what we say is their properties are also more or less alike. Even if we are talking about the 2 prices, more or less, let's say we are talking of these 5 as the prices of the products. If these 2 are more or less similar, we say that their behavior is also more or less similar. So that is the basic concept that we are talking of. Even attitudes wise, if these 2 people have similar kinds of attitudes, then some other commonalities also can exist between these 2 groups. So that is the basis. So things which are alike, they are most likely to have similar kind of properties. So when we are talking about classification here, in this algorithm, we are trying to identify, so if I am talking about a new data, I will try to see which is the closest one to this new data out of these existing data, right? So in short, if I have to understand, I will see with respect to the various properties of this new data or new record, I will try to see which one is the most similar or the most nearest in various properties with respect to this new data. So let's say if this is the most similar one, then whatever is the classification of this particular element of this particular record, I will try to assign it to this particular record. So I'm doing the classification by placing it into a category. I will place this in a category with the most similar or the nearest neighbors. So I'll try to identify the nearest neighbors. When I use the word nearest neighbors, those particular records, those particular elements from the existing data which are very closer to this new data. Those are the ones I am calling as the most similar or the nearest neighbors. So I'll try to classify the data by placing this into a category with the most similar or the nearest neighbors. So that is the basic mechanism of the nearest neighbors algorithm. So we need to understand the key concepts that define the nearest neighbor classifiers. So the definitions and other key concepts we would be covering in this session. So different kinds of methods which define the similarity. How do I say these 2 are closer, these 2 are far off? So there is a kind of a distance computation. So we need to understand the distance computation. And once we are aware of the various conceptual aspects, we will take an R implementation of the K nearest neighbors algorithm and try to take an example to do the classification. So by now you got a clarity. The way the nearest neighbor algorithm classifies the data. So any new cases that I am taking, they are assigned to the class of the most similar case, right? So I will try to see for the new case that I have taken up, I will try to see among the various existing cases which k cases are most closest to this new case. So based on these k cases, let's say if I'm talking about k as 5, which 5 cases are the most closest to the new cases? So let's say out of these 5 cases, 4 of them belong to the group 1 and 1 of them belongs to group 2. So because the majority of them belong to group 1, majority of the ones that are similar are the closest or the nearest neighbors to this new case are belonging to group 1, even the new case will be classified into group 1 itself. That is the typical way the nearest neighbors classifiers are defined. So we have so many applications again, right? Computer vision applications, optical character recognition, facial recognitions, and lot of other applications where we are doing classifications. If you look at identify the patterns in the genetic diseases used in detecting specific proteins, diseases, lots of applications in the medical world, in the imaging world, you can think of lots and lots of applications. So we are trying to identify all the closest neighbors to the new data set, and based on those closest neighbors we are trying to identify what is the classification of that closest neighbors, and depending on the majority of the classification we are assigning the class for the new data as well. So these kind of methods are very well suited for the classification tasks where huge amounts of relationships are existing between the various features. There is a lot of interrelationship, there is a lot of correlation between the various features that are used to define the class. Target classes are numerous, there are so many target classes. There is a lot of complication in terms of the target class. Very difficult to understand the relationships between the variables. In those cases, it's better that I rely on the nearest neighbors algorithm to typically do the classification of the data. So coming to the KNN algorithm, right, we need to talk about the strengths as well as the weaknesses. One, it is very simple, very effective. So this is one kind of an algorithm which does not make any kind of assumption regarding the distribution of the data. Majority of the algorithms, they are parametric, means they make assumptions that this particular data follows, let's say, a normal distribution or a uniform distribution or a log normal distribution or a Poisson distribution, something like this. Whereas the KNN algorithm does not make any kind of assumption regarding the distribution of the data. So whatever is the type of the data, I can use this algorithm as it is. I really don't need to check whether the data is normal or not, whether the data is following some other distribution or not, because this model is a very straightforward model. It does not assume any particular distribution associated with the data, but at a later point you would be seeing that many other distributions that we are going to look at, many other algorithms that we are going to look at, make explicit assumptions associated with the distribution of the data. So we have to be very careful regarding the pluses and the minuses of each of the algorithms. Now, this is having a very fast training phase. We will be seeing slightly in a while from now. It does not create any kind of a model. When I say does not create any kind of a model, there is no formula or there is no equation that comes out of the learning process. So there is no generalization phase in this particular mechanism at all. There is no abstraction phase at all, because I am not creating any kind of a formula out of the data that I am being provided. So that's the reason what it typically does is it actually dumps the whole data in the memory. No abstraction, no generalization. And because of that reason, the training phase is much faster. But the classification phase is very slow, because if it has to do the classification of one new record, it will compare this one new record with all the 500 existing records. Let's say we have 500 existing records in the data. So the one new record for which I want to do the classification, it will compare this with all the 500 existing records. Then it will identify which k items are the nearest neighbors to this record, and based on that it will see the class of these k items, and whichever the class is the majority class, it would do the classification accordingly. So for each new record, this is the total process that happens when it has to do the classification. So that's the reason we say the classification phase is very slow. And because it does not produce a model, so new insights are not coming out from the data. No generalizations being done, no patterns being stored, no formulas being created. So the novel and the new insights from the data are not coming up. Explicit relationships among the various features are not getting displayed for us. Right? So we have to understand the limitations of the mode as well. And it takes a large amount of memory, because every item is compared with all the existing records. So that much of processing is required, that much of memory is typically being consumed. So it requires powerful systems for execution. And the main drawback here is if my features are nominal features, right, which are more categorical, non-quantitative. If the features are non-quantitative or non-continuous kind of features, it would be very difficult. We need to have different mechanism to process them, because the KNN algorithm cannot do the processing of that kind of a data. And even if my data is having some missing values, even in that case it would be difficult to execute this algorithm. So I have to take utmost care while using this algorithm. I have to make sure that no feature is a nominal feature. I don't have any missing data. I have to clean the data for all these things before I get into the execution of the KNN algorithm. Now coming to the algorithm, just like with any other algorithm, I have to begin with a training data set. So I will begin with a training data set. So the total data set that I am having, I will split it into the training data set and testing data set. As I have indicated to you earlier also, approximately 70% of my data is a training data, 30% of the data is a testing data. So I will be looking at the cases which are classified into various categories. So this could be belonging to group 1, group 2, group 3, different kinds of categories of data I would be taking. I would be typically starting with the training data. Then whatever is the testing data that I have, I will take each element of this testing data, each observation of this testing data. I'll take all the records. I will try to understand the k records in this training data which are closest to each of these records. So that k I have to specify in advance, whether it is 3, 5, 10, 20, whatever it is. Now for each data that is there in the testing data set, it will try to identify the k nearest records which are more similar to the record in the test data. So those are the k nearest neighbors for this particular test data. Then there will be k nearest neighbors for this record, k nearest neighbors for this record, and so on. Now out of these k nearest neighbors, I will try to identify which class is the majority, and So that particular class will be assigned to this new record of the test data. That is how the KNN algorithm is going to be executed. Once we take up a data set and once we execute it, things become more and more simpler for you. Now, in all this process, when we are using the word nearest neighbors, there should be some kind of mechanism to compute the nearest or the farthest, right? Now that is being executed through the distance function, a formula that is measuring the similarity between the two records. How close they are or how far they are is typically being measured through the distance function. There are various ways of computing the distance, but the most prominent mechanism and the one that is typically used by my KNN algorithm also is the Euclidean distance. So which is more like, if I am talking about 2 points x1, y1, z1 and x2, y2, z2, the distance between these 2 points is nothing but square root of x2 minus x1 whole squared plus y2 minus y1 whole squared plus z2 minus z1 whole squared. So it's basically nothing but the square of the differences, sum of the square root of the sum of the squares of the differences is what is the definition of the distance. This is what in coordinate geometry also we would be using this as a formula. If we are using a ruler to connect 2 points, typically called as the aerial distance between the points, it's the shortest direct route. So this is the distance that we are typically using, and based on this distance computation, if I am having 10 different features, on all these features I would be doing x2 minus x1 whole squared plus y2 minus y1 whole squared plus so on, add up all the squared distances and finally take the square root, which I am calling as the distance between x1 and x2, or distance between p and q, some kind of a distance between the two observations. So whichever is the observation that is having the least amount of a distance, I would be classifying it as the nearest neighbor. Now that I have identified that for each record in the testing data, I have to identify k records in the training data which are very closest to this record in the testing data. Now, how much should be the value of k? Should it be 1? Should it be 2? Should it be 3? Should it be 10? So deciding how many neighbors to use determine how well the model will generalize, which means I would typically play around with the value of k so that I would get the best possible estimate out of the test data. I have to get as much of generalization as possible on the test data, as much of accuracy as possible on the test data, so that I can launch it to the production data quite comfortably. But remember, there is always a balance between overfitting and underfitting. See, if you are having large number of values of k, right? Let's assume that I am having, or let's take the other way, small k. Let's say k is equal to only 1. So 1 nearest neighbor is what I am trying to find out, and whatever is the group of that nearest neighbor, I will assign it to my new data. So based on the class of 1 closest value, I am directly assigning that particular class to my new data also. So there is a lot of bias for me. I am having undue influence. So whatever is the class of this, I am assigning it to the new data as well. So if this is a very much biased kind of an example, then probably this classification will be more and more biased. So there is a lot of noise. Outliers will pull all the data closer to them. All kinds of classifications will come very absurd. Whereas if k is very high, right? Let's say if I have 500 records, I am setting k also as 500. So all the 500 would be the nearest neighbors, because I want 500 nearest neighbors. All the 500 records will be the nearest neighbors to the new record. So depending on how many are there in each group, obviously if all 500 is the training data set, and let's say if 300 belong to group 1 and 200 belong to group 2, because majority of them belong to group 1, every new item will be assigned to group 1 only, because there is no way group 2 can come up in this process at all, because all 500 are nearest neighbors. So out of this 500, 300 of them are group 1. So even all the new ones will belong to group 1 itself. There is no way I am going to get the group 2 at all. So I'm completely ignoring the small but important patterns in the process altogether. So I need to really have a trade-off between the large value of k versus the small value of k. Typically, people suggest if your training data is having a size n, generally you try to choose your k very closer to square root of n. Right? Though you can set anywhere between 3 and 10, but generally I suggest take the square root of the number of training cases to be an appropriate value of k, but you can very well play around. You can change the values of k, you can take different values of k, and for different values of k, see the amount of accuracy. For different values of k, see the amount of accuracy that the model is generating with respect to the test data. The more is the accuracy that the test data is coming out with, probably you can narrow down on that value of k. So this is where I was saying, test several k values, different variety of test data sets, and choose the one which has the best classification performance on the test data. So choose a larger k, right? Look at which one. So in some cases people can even look at a weighted voting rather than one vote for each one. So vote of the closest neighbors is more and more authorized, whereas the vote of the records which are far away, which are further away neighbors, the weights of them should be considered to be much lower. So that's the kind of a weightages I can give, rather than saying one vote for each neighbor. I can give a kind of a weighted votes for each of the neighbors. The closest neighbors will carry more weight. The further away kind of neighbors will carry the least weights out of all the different neighbors. So that's one more important aspect as a part of this building the KNN algorithm. Now, before we start running the algorithm, a few important aspects, especially only for this KNN algorithm, are there. We need a few data preparation aspects for using the KNN algorithm. First thing is transformation. See here, because it uses the distance, right, x2 minus x1 whole squared plus y2 minus y1 whole squared, and we are talking about the square root. Let's say x1 is 5 some units, x2 is 10, whereas on the other side y1 is 1000, y2 is 1100. Now if you look at x2 minus x1 whole squared, it's only 10 minus 5 whole squared, which is 25, whereas y2 minus y1 whole squared is actually 10,000. So the overall distance is becoming 10,025 under root. Now you could see this is dominating the distance quite heavily, whereas the contribution of distance for this particular variable is very small. Whereas if you observe the variables, for the second record, the value is double to that of the first record. Whereas here, the second record is only 10% above the first record value. Whereas here it is 100% above. Now, because of this, what happens is the size matters a lot here, right? Size is playing a major role in terms of the determination of the distance. So that particular variable, which is having a very big value, is going to dominate the distance altogether, which is what will create all the problems in terms of classification. So to avoid this size matters kind of a problem, people came out with a mechanism where we are transforming each and every variable into a standard range. So there are, which is what we call as transformation, or typically we call them as normalization mechanisms, so that all the observations will carry a uniform kind of a range. Size does not really matter in these aspects. So that is the first step we cannot ignore when we are using the KNN algorithm. So what kind of mechanism we have to use for it, we will look at it, but transformation is a must when we are applying the KNN algorithm, because distance formula is completely based on the size of the observation. Now if a particular observations are having higher values, obviously they will influence the distance much heavily compared to the other values. So we are doing a rescaling of all the features such that all of them contribute relatively equal to the distance formula. And to accomplish that, different kinds of transformations we talk about. Here I am trying to bring two such kind of transformations. One is called as a min-max normalization. We will try to adjust all the values. It's a traditional method of rescaling all the features for KNN. KNN generally prefers the data to be given in this kind of an input. So it is transforming all the features such that they lie between only 0 and 1. Even if it is 5 and 10 or 1000 and 1100, they are adjusted in such a way that they lie between 0 and 1. So for that, the new values are typically created, wherein we take x, which is the observed value, minus the minimum. So we subtract the minimum from each observation and divide it by the difference between the maximum and the minimum, which is the range of x. Now by doing this, the values will lie only between 0 and 1. The minimum most value will have a value of 0. The maximum most value will have a value of 1. But none of the values will go below 0 or above 1. That way, every column I am able to bring that into a range between 0 and 1 itself. So because of that reason, the size of that particular variable hardly matters. So how far from 0% to 1% a particular value is lying? That's a simple way I can interpret that stuff. So that's one kind of a normalization I can do with the data. Or the second form of normalization that I can think of is a z-score based standardization, where from each observation I subtract the mean of the whole variable divided by the standard deviation of the particular variable. So this is also a kind of a rescaling, so which is typically done in terms of number of standard deviations above the mean or below the mean. That particular data, every particular data, I would be seeing how many standard deviations is it above the mean or how many standard deviations is it below the mean. So that is the kind of a z-score computation that we need to do. And once the z-score standardization is typically done, I will use that data for the KNN. So basically, if I see that my data is having some kind of size issues for different variables, either I perform a min-max normalization or I perform a z-score standardization before giving that data for the application of the KNN algorithm. But in z-score, we have to understand the negative and positive numbers, we don't get the values between 0 and 1. Generally, you get numbers between -3 to +3. Of course, there will be a few below -3 and there could be a very few of them above +3. Theoretically, it's an unbounded range of negative and positive numbers, but you will find more than 90-95% of the observations between the -3 and +3 limits itself. So this kind of a standardization also can be very well performed with the data. Then, one more data preparation aspect that we would be doing is if there are nominal variables present as a part of my data. We have already discussed earlier that KNN does not handle the nominal data. So this is where we bring in a concept called dummy coding. Dummy coding is nothing but, if I am talking about three particular variables, let's say we are using a variable called marital status, which has three variables: single, married, divorced. So this is the marital status which is having three categories. Now if I want to compute the Euclidean distance, it's not defined. Probably I may say this is 1, this is 2, this is 3. Someone else may say this is 1, this is 2, this is 3. Someone else may say this is 1, this is 2, this is 3. So computations will be different for each one of them. So I can't use directly the Euclidean distance formula for a nominal data. So I am converting this into a number. Now the way I convert them when we are talking of dummy variables is, out of these three categories, I will create n minus 1 new dummy variable. If there are n categories, I will always create n minus 1 new dummy variables. So let's say I create a dummy variable called single, I create a dummy variable called married. So I'll get a new column called single, whose values will be 1 if this categorical variable is having a value single, otherwise it will have a value of 0. So not single, so it will become single or not single. So not single could be married or divorced, but it is not single. So single will have a value 1, not single will have a value 0. Similarly, I'll create another variable called married. So if a person is married, the value is 1. If a person is not married, the value is 0. Now I don't need to create for the third variable, because here if single is 0 and married is 0, automatically it would be treated as a part of divorced itself. So if I am having n category nominal variable, I will be coding it, I will be doing a dummy coding. Dummy coding is nothing but it will have a values of only 1 and 0. So it's a binary indicator variable that would be created for each of such kind of categories, and I would be creating them for n minus 1 levels of this feature. So this is a massive task that is there for me, converting all of them into binaries before I can use the KNN algorithm on my data. And now the distance, so in case of dummies, in case of nominal variables, the value will be either 0 or 1, which means this also will lie between 0 to 1 itself. So I don't need to do any kind of min-max normalization again, because min-max normalization also brings the values between 0 and 1 itself, and these values are also between 0 and 1. But of course, if I want to do z-score, then probably I have to do the conversion for this variable as well. So these are some of the basic data preparations. When we take the data, it will become more and more clear and simple for you. But these are some of the important data preparations that I have to take care of while I have to use my KNN algorithm. Before I go ahead in terms of using the KNN algorithm, these data preparation steps are very much essential. Now, before we actually start working with the data, we'll just try to understand, why do we call this KNN algorithm as a lazy learning process? By now you must have already got it. One, it is not creating any kind of a model. So there is no abstraction at all, no learning at all, no generalization. All it is doing is it is storing the data as it is. So there is really not any kind of a real learning. When there is a learning, we have already indicated that there should be some kind of a formula, there should be some kind of a diagram which will explain the way it has abstracted the data. But here we don't find any such kind of stuff. That's the reason we call it as a lazy learning process. So the training phase is much faster because there is no abstraction, no generalization of the data. But of course, if it has to make predictions, it's very slow because every observation is in the testing data is compared with all the observations in the training data, and then the nearest neighbors are identified and their majority class is typically assigned. So it's a very clear non-parametric learning method. So there is no computations that are involved, no model that is built. So no specific learning that is coming from this model. So there is no way you can understand also how the classification has typically worked. If there are parameters, if there are formulas, then you can really make out which variable is significantly influencing the group, which variables are insignificant in doing the classification. So those kind of things we could have understood if it is a parametric method. Because there is no formula, there is no way for me to understand which variables are important in the classification process, which variables are unimportant in the classification process also. So there is no fitting, there is no assumption. So there are regarding the distribution of the data, everything is in nothing is preconceived form. So we are trying to find out the natural patterns in the data. So we are not doing any kind of forcible fitting of some kind of a distribution to a data. We are trying to find as many natural patterns as possible in the data itself. That's one more advantage going ahead with the KNN algorithm. Though it is lazy, we still keep using it because of these kind of advantages that this algorithm is generating. Now that we are having a clarity in terms of the conceptual aspects regarding this particular algorithm, now I suggest we take a example data. Based on this particular data, let's try to do a full-fledged implementation of the KNN algorithm. I've classified the whole process into different steps. So we'll try to execute step by step to see how KNN is working, what is the level of accuracy that is associated with the KNN algorithm in terms of classification of the testing data, right? So let's go ahead with the example. So now for executing this, let's take a data set, right? I'm taking a credit data that is available that I have downloaded from a public source. So this credit data, right, finally has a variable called default. So if you look at the data, there are close to 1,000 records. There are 1,000 customers data, and whether they have defaulted on a loan or they did not. So this is the class I'm interested in predicting, whether a particular person will default on a loan or he or she will not default. So this is relating to some German data. So we have the data in terms of Deutschmark, which is a very old data out here. So some of the variables people have brainstormed, which they said they would influence the default, are the checking balance. So there are different kinds of checking balances. One is less than 0 dm, 1 to 200 dm, unknown. A few of these variables are there, right? Similarly, a month loan duration. So how long back the loan has been taken? 6 months. So is the loan taken for 6 months, 48 months, 12 months, 42 months, and so on. The credit history of that person, critical, good, poor, there are some kind of classifications there, perfect. The purpose for which the loan has been taken, furniture, appliances, education, car. So there are different purposes for which people have taken the loan. The amount that has been taken in the form of loan, the savings balance in the savings account. So these are the balances. For some of them it is unknown. The employment duration, so 1 to 4 years, 4 to 7 years, greater than 7 years, less than 1 year, different kinds of categories are there. Remember, these are all nominal variables only. Even this one, this one, this one, this, they are all nominal variable. So if I have to use all these variables for my KNN algorithm, I have to create dummy variables for each one of them. Okay, the percentage of income which they have typically done the borrowing, 4%, 2%, 2%. So this is the percentage of income that they have borrowed. The years at the current residence, 4 years, 2 years, 3 years, some such kind of a data. The age of the person, old, young. If they have some other kind of credits, so you have bank, none, some other things. The housing, own, other, rent, some other stuff. Existing loans, 1, 2, 3 kind of stuff. The kind of job they are in, skilled, unskilled, so different kinds of groups. The department, so there are different kinds of departments. And do they have a phone, yes or no? All these things are expected to influence the default, whether a person will default or not default. So that's the reason historically 1,000 records have been taken by the bank, and whether they have defaulted on the loan or they have not defaulted on the loan, and along with that it wants to find out the relationship between the default and these various attributes, right? They want to look at the relationship between the default and this various attributes. So given one person, now if I bring in a new customer, right, whose checking balance is something, whose month loan duration is something, credit history is this much, taken a loan amount of this much for this particular purpose, all these things, I really want to see whether this person would be a default or he would not be a default. How do I really classify that person into a default or a not default, going with this K nearest neighbor analysis? So that's my typical objective. So for that reason, what I would like to do is I want to get that data into R. So I am reading that particular data into a variable called credit. So this data is present in my CSV file, which is present on my H drive. So I am doing a read.csv, getting this data into the variable called credit, right? So now the first step, so I have collected the data. Then I am doing the exploration of the data. My second step is I have to start exploring it. When I am saying exploring, I have to look at the structure, STR of credit. Okay, so the checking balance is a factor with 4 levels: less than 0 DM, greater than 0 DM, right, and couple of other levels. So I want to look at the checking balance, which is a factor. Month loan duration is an integer, so if I want to keep it as an integer, I can very well keep it like this. Credit history is a factor with 5 levels. So if I have to create dummy variables, I have to create 4 dummy variables for this. Similarly, purpose is a factor with 6 levels, so I have to create 5 dummy variables for this. Amount is an integer, fair enough. Savings balance is having 5 levels, so I have to create 4 dummy variables. Employment duration also is having 5 levels, so I am creating 4 dummy variables for this. Similarly, percentage of income is an integer, so I'll keep it as it is. Years at the residence is also an integer. Age of the person is also an integer. Other credits, there are 3 levels, so we have to create 2 dummy variables here. Similarly, housing is also having 3 levels factors, so I have to create them as 2 dummy variables. Existing loans, it's an integer, so I'll keep them as it is, because my KNN algorithm will not be able to handle all the nominal variables properly. So job is a factor with 4 levels, management, skilled, etc. So I'll create 3 dummy variables. Phone is a factor with 2 levels, no S. So does not matter. I can very well keep them as it is itself, because I need one dummy variable. So I can very well keep the things as it is itself. Right? So this is the structure. I have understood the structure of it. So there is no ID related variable here. If there has been any kind of ID related variable, I would have directly deleted the stuff. But because there is no ID related variable, I am not deleting anything from here. Then first thing is, look at the frequency and proportion of the outcome variable. The outcome variable is, I am trying to predict the default. So let me see, out of that 1000 records, what is the distribution between no and yes, or even we will look at for all the variables. So let's do a simple summary. The summary of credit, right? It gives me for all the output as well as input variables. So I will say less than 0 dm, there are 274 observations. Greater than 200 dm, there are 63 observations, and so on. If it is a quantitative, if it is a categorical variable, it will be doing the frequencies and counting. We have already seen that. But if it is a quantitative variable, it would be computing the minimum, maximum, mean, median, first quartile and the third quartile. Now look at the default. There are 700 of them who have not defaulted. 300 of them have defaulted. So probably 30% of the total set of customers have defaulted. So it's a very big default. So I really need to have some kind of a mechanism which can very well identify what kind of people are going to default, so that I can try to reduce this percentage by filtering out those kind of people who may default in the future, and try to reduce this percentage of default altogether. But before I start using the normalization feature and all, I have to initially start off with the dummy variables creation, right? So I have to create the dummy variables. So let's create, there are no NAs anywhere, no missing values. If the missing values are there, here it would have shown NA as one more variable or one more row in any of these data element. So because there are no NAs, there are no missing values in the data. But yes, let me try to see if I can try to create the dummy variables out of each one of them. So one way is that, or the other way is I should not consider this nominal variables as a part of my model building process at all. But rather than that, let's quickly try to do dummy variable creation for each one of them. Right? So let me look at the credit history first. So I'll say credit dollar or let me go with credit new. I'll call a new variable called credit underscore new, where I'm taking from the credit, I'll take a subset first. All the numeric variables, I'll take them as it is. So all the rows I will take, and columns wise I will be taking column number 2, which is the monthly loan duration. 3 I will not take, 4 I will not take, 5 I am going to take the amount, 6 I will not, 7 I will not, 8, 9, 10. So 8 to 10 I am going to take, 11, 12 I will not, 13 I will, 14 I will not. 15 I'm going to take. Probably 16 also I'll take it as it is, because anyhow it is yes or no, 1 and 2. So hardly matters. So it's already one single dummy variable. So let me take it as it is. So all these columns I'm going to take and consider it as credit underscore new. Now I will keep adding the variables here. Credit underscore new dollar, credit underscore or probably I'll call it as credit history underscore critical. Right, I'll find out the credit history underscore critical. I'll use a function called if else, wherein credit dollar credit underscore history is equal to critical. Right, when credit underscore history is equal to critical, I will set it as 1, otherwise I'll set it as 0. So that's how I'm creating the credit underscore new credit history underscore critical as a variable. So I'm comparing this with critical, and if it is critical I'll set it as 0, otherwise I'll set it as equal to 1. So just to check out this particular stuff, let's do a quick summary of credit underscore new. Once we get this story correct, we can do this for all of the variables. So now you could see here credit underscore history critical is having a mean of 0.293. Out of the 1000, 29.3% of the observations are 1, all others are 0. So you see 0 to 1 kind of stuff. So this is working. So this is where we'll start creating new variables. Credit underscore new credit history underscore, instead of critical now, let me set it as good. And if else credit history is equal to good, I will make it as 1, otherwise I'll make it as 0. So I'm creating a new variable called credit history good. The same way now let me change it to perfect. I'll create another new variable called perfect, and here also I would be considering it as perfect. Right, so I should get 40 of them in that particular class. Then probably I am calling it as poor. So the last category I will not consider, which is very good. That is like a default for me. Right, so I am making it as poor. So these are the 4 groups that I am bringing in. Right, so I'll get 4 new columns. So the credit history part is handled now. Let me do the checking balance part, because there are 4 categories. I need to create 3 dummy variables. So I'll say, instead of this, I'll say checking balance underscore LT 0 DM, less than 0 DM. Right, and I will be setting this particular variable, instead of credit history, I will be checking for credit balance value. Instead of poor, I'll try to set it as less than 0 DM. So this would be your coming out. Similarly, I can very well create greater than 200 DM. So I'll call it as GT 200 DM. Checking balance, instead of putting less than 0 dm, I'll put it as greater than 200 dm. So this is one more variable that I'm creating, and probably I would also set it as unknown so that the other one would be my default variable. So let me set it as unknown so that even the balance I can set it equal to unknown. Right? So these are the new variables that are getting created. Just to quickly check out the process, let me look at the summary of this. So the summary is coming out quite proper, right? I could see, depending on number of variables that are falling in each of the categories, the means are more or less reflecting them. So the remaining variables also I need to create the dummy variables in the same way. So let me again load the credit. So credit balances part is done, credit history part is done. Now I have to work with business itself. So let me start working with the purpose. So I'll call it as purpose underscore business. So credit dollar purpose is equal to business. So this is one more variable that I have created. Then again I'll set it as car. Probably there is car and car 0. Let me use both of them as car only. For simplicity purpose, I don't know why is this car 0 coming up. So here also I'll use car. Right, if else credit purpose equal to car, set it as 1. Similarly, I'll put if else, one more variable I'm setting, credit purpose equal to car 0. Car 0 also I will set it as 1 else 0. So in both the cases I am setting it as car only. Right? Similarly, I'll have education. So purpose I'm setting it as education. Even that education will be either 0 or 1. Similarly, I'll use renovation so that the furnitures or appliances will have furniture and appliances will be treated as default. So let me do renovations as another variable. So this kind of dummy variable creations I am typically performing. Then amount is fine, savings balance also. The same logic I have to apply for savings balance. Right, so let me call it as savings underscore balance underscore LT 100 DM, wherein I'm setting if else this particular value is equal to less than 100 dm. This is equal to less than 100 dm. I am assigning this value as 1, otherwise I am assigning this value as 0. Similarly, I am talking about greater than 1000 dm. So I'll set it as greater than 1000 dm instead of less than 100. I'll have to set this as greater than 1000 dm. Right, this if I have to use a very perfect classification example, I have to do all this work. This is a kind of initial workout that I am supposed to do. 100 to 500 dm. 100 to 500 dm. Where in this balance I am setting it equal to 100 to 500 dm. Probably we'll save this data so that for all other purposes we can very well use it at a later point. Then I will also set it as 500 to 1000 dm. 500 to 1000 dm, where again I am setting the statuses here as 500 to 1000 dm. So this is one more new variable that got created. Similarly, I have to go ahead in terms of understanding the employment duration as well. Now let's go to, instead of saving balance, let me create new variables associated with employment duration. Let me call it as employment LT1, which is less than 1 year. And here I will take it as credit dollar employment duration is equal to less than 1 year. Right, so this is one more group that is getting created. Now I can redo it, greater than 7. So I'll call it as GT7. Again the same, duration instead of less than 1 year, let me call it as greater than 7 years. One more group. Similarly, 1 to 4, instead of GT7, I'll call it as 1 to 4. And this one I would map it to 1 to 4 years. So there are 339 people falling in that category. And similarly, I could also set it as 4 to 7. 4 to 7, wherein I am mapping this to. So you have to do this exercise for all the categorical variables if you are looking at much better results out of your process. So I don't need percentage income, I don't need years at residence, I don't need age. I have to look at other credit, right? One more variable that I have to look at, which is the other credit. So let me start using this other underscore credit, and underscore I'll put it as bank. So wherein this particular variable would be dollar other underscore credit is equal to bank. So this is one more variable that we have newly created. And similarly, I can look at store. Let me call this as store. So even this one I would equate it to store. So this is one more variable that got created. So I can take care of this part. Now again, housing is also one more variable which we need to bring in. So because there are 3 categories for housing, I should look out for 2 dummy variables. So let me call it as housing underscore own, right? Housing underscore own, wherein I am trying to compare it with dollar housing. and equating it to own. This is one new variable that is getting created. And similarly, housing underscore rent, another new variable that I am creating, wherein I am comparing it with rent. So another two dummy variables getting created for housing. And finally, I also have it as the job. So because there are four categories per job, we require three dummy variables. So once I create it, I think we are done. So let me do checking underscore job underscore management, where I am trying to map it. The job is getting mapped to management. So this is the process that we are creating for the dummy variables. Right, I will also add the skilled. So you can directly use this ready-made piece of code, right? You can skip this process. And even unemployed, one more thing that I can look at. All other things, the default here is the last category, which is unskilled. So I'll take it as unemployed, where we have only 22 people, but let me take it as unemployed. Okay, so now all the other things are typically done. So let's quickly look at summary of credit new. So this is the one that we are going to work with, because one, all the numbers are pretty much clear out here, and all the nominal variables we were successfully able to do a quantification by creating dummy variables for all these variables. So this is where our initial processing part is taken care of. Every variable now is converted into a numerical variable. Now I have to apply normalization, right? As we have already discussed earlier, I can use either a min-max kind of a normalization, or I can use a z-score normalization. Initially, I want to use a min-max normalization, but unfortunately, the min-max normalization is not available as a direct formula in the base R. So we will have to create a function. So let me call a new function called normalize. That's the new function I will call. So I'll create a new function of x. Right, I'm creating a new function of x. Now I know the way to compute the min-max normalization. We have already discussed the formula for it. X minus minimum of x divided by the maximum of x minus the minimum of x. That is what we are calling as the normalize. So the same function you apply it here. So write it as x minus of minimum of x divided by the maximum of x minus the minimum of x. So this is what is the way you have defined the function called normalize. So let's close the bracket so that the function is typically executed. So we have created a normalized function. So if we want a min-max normalization, I don't have a direct formula in R. So I am writing my own function based on the theoretical formula that I am already aware of. But if I want to do a z-score normalization, we have a formula called scale. So when we do a z-score normalization later to compare between the models, we will use a scale function. But now, once we have created this formula, now I want to apply this formula to almost all the columns of my data. All the columns that are there, I want to apply this normalization, the min-max kind of a normalization. So if I have to apply to all the columns, all I am doing is I am saying use lapply. So I'm using lapply as a function. Of course, here we don't have the default. I did not capture the default out here. So I don't have the default related data, which is my dependent variable out here. So I don't need to bother much about it. So for all the other variables which does not include my decision variable, I'll be using lapply for it. I'll be using for all my variables except the dependent variable. Anyhow, as a part of credit new, I did not capture the decision variable, so I don't need to bother much on that aspect. So I will typically take lapply all the columns. So I will be using for all the data, right? So I'll have to use it for all the columns. So I'll say credit underscore new, and the formula that I'm applying is normalize. But remember, when I'm using lapply, obviously the output is coming out in the form of a list. But I don't want the output in the form of a list. I want it in the form of a data frame. So whatever the output that is coming in the form of a list, I will be converting it into a data frame using as.data_frame on the top of it. So as.data.frame, I'll be using it on top of the lapply function. So I'll be using as.data.frame on the top of the lapply function, which would convert or which would apply a min-max normalization to each and every column of the data, which will apply the min-max normalization to each column of the data. And it's better to store this particular value as a part of a new variable rather than simply displaying it. It's better that I store this as a part of the new variable so that my existing data also is present and my new data is also present. So that's where I'll call it as credit M, which is indicating that credit, or probably for more clarity, let me call it credit min-max. So I'm using a credit min-max as the name of the variable, which is converting it into a data frame after the application of the lapply. So this storage of credit min-max will have all the values between 0 and 1 only. Let's try to see that. Summary factor not meaningful for the factors. Credit min-max, I'm applying it So let me look at the structure of credit underscore new so that we'll see which factor variables are there still. So let me look at credit underscore new, the structure of it. All our numbers are okay. The phone is still a factor. So it's better that I convert the phone also before I apply this process. Let me apply credit underscore new, probably saying phone, credit underscore new $phone. I will set it equal to 1 if it is equal to yes. If it is equal to no, I'll keep it as 0 itself. So let this be one more new column. Now when I am redoing the structure, I see that all of them are either integers or numbers. So because of this, I should really see that my credit min-max this time, the normalization process should work quite comfortably. Yes. Now the credit min-max normalization is applied to the data. And if you are trying to look at the summary of this credit min-max, if you are looking at the summary of this credit min-max, you see for all these variables, minimum value is 0, the maximum is 1. across you would see the similar kind of behavior. The minimum value is 0, the maximum value is 1. So we have scaled the data such that all the variables lie between 0 and 1, and size really does not matter out here. So while building the k nearest neighbors algorithm, the size of the data really does not matter because all the variables have been converted into a 0, 1 kind of an interval. Now the same process we can follow for creating them into a Z scaling as well. So if I have to do a Z scaling, the whole thing is I will create, instead of credit min max, I will create another new variable called credit Z score. But here I don't need the L apply and all. I have a direct formula. So I'll use a direct formula called scale, and I'll pass the variable, the whole data frame, credit underscore new. The whole data frame I'll pass it as an input to this scale function. Now if you look at the summary of credit Z score variable, which we will be using later, now we will not use it, but the credit min max is doing a min max normalization of each and every variable. Credit Z score is performing a Z score based normalization for each and every variable. Now you could see when you have performed a Z score, you will find that the mean is 0 in all the cases, because in Z score, if you remember, the Z score is computed as every observation minus the mean of the observations divided by the standard deviation of the observation. So the Z score is typically computed through this mechanism. So because of which you see the mean is 0 for all the observations. The values are between some negatives, some positives, but majority of them you will find that they lie between -3 to +3 itself. Very rarely you have a few observations which are much above the +3 range or much below the -3 kind of a range. So which means we have brought the data more or less into a similar intervals so that we can apply our k nearest neighbors algorithm either to the first or to the second normalized data. So we'll apply both of them. We'll see which one is more appropriate for this particular data. So we are confirming the transformation. That is what we have done right now by looking at the variable summary statistic. So if I have done a Z score transformation, I should see that the mean value should be 0 for all the variables, which it is here. If I have done a min-max normalization, I should see that the minimum value should be 0 and the maximum value should be 1 for each and every variable separately. And we have ensured that, which means this step is quite successfully accomplished. Right? So now let's move on to the next step. Alright. Now, once this step is done, let's move to the next step where I am doing a data preparation. For data preparation, I have to create a training data set as well as a test data set. So I will be splitting the whole data. Right here I have 1000 records of data. So 70% of it approximately, which is 700 records, I'll be treating it as a training data, and 300 records I'll be taking it as a testing data. So the training data set will be used to build the KNN model, and the test data set will be used to estimate the predictive accuracy of the model. What is the predictive accuracy of the model? Is it 70%? Is it 80%? Is it 90%? So the higher is the predictive accuracy of the model, I will be using this model for testing the credit worthiness of the newer applicants. Whereas if it is much poorer, then I cannot use this model for estimating or for predicting the default behavior of the new application. So I have to perform this division in a very random manner. So let's do a few things here. Here I would take the help of a function called set.seed. See, basically I would be using a sample function to generate a random, to pick randomly some 700 observations between 1 to 1000 without any duplication. That is what I want. The sample function, what it will do is, so it will say you take a sample from 1 to 1000, out of 1 to 1000 chits, you pull 700 chits wherein there is no replacement. Replacement is set to false, which means no value will be repeated twice. So that is what is the job of a sample function. So randomly some 700 observations will be pulled and they would be assigned to the training data. Right? So the training as a value will assign some randomly 700 values out of this from the 1 to 1000. But in many cases, I see every time I do this sample, I'll get a different set of 700 altogether. So to make sure, especially if I am using two different models, now I am using a KNN algorithm. Let's say tomorrow I want to use a decision tree algorithm. And I want to see out of these two, which one is having a high predictive accuracy. In that case, I don't want a different 700 to build this model and a different 700 to build this model. I want the same set of random 700 to build this model as well as this model. The same 300 should be used to test this model as well as test this model, so that the randomness of the data will not cause a bias in my decision process. So to take the same set of random variables, random numbers, we generally set a seed to a particular number. So in this case, let me use the set.seed as 100. So now whatever the random number that is generated, it would be the same. Whenever I set a seed of 100, it could be any number. There is no meaning to that number. You set it to any integer. But whenever you set the seed to that particular integer, the set of random numbers the system would be generating for you is more or less the same set. Because the random numbers that are generated by the system generally are pseudo-random numbers. They are not perfect random numbers, which are based on some algorithm that is dependent on the seed value itself. So otherwise it would take a random seed, but because we have set the seed as 100, based on this the random numbers would be computed for us. So what we can do is, for this algorithm I would use the seed 100. Even tomorrow when I do it for decision tree, I would use the same seed of 100, so that the same 700 random numbers would be generated. The same 700 would be taken as a part of my training data set as well. So this is where now I will take, now that I have set the seed at 100, I will create a variable called train, which is a sample out of from 1 to 1000 numbers. Take a sample of some 700 numbers where replace equal to false, means there is no duplication. If I am fine with duplication, I will set replace equal to true. But here I don't want the duplication, so that's where I have set replace equal to false. So this is what has come out as a part of my training data. So let me just check the train. So you could see it has generated 700 observations from 1 to 1000. So first it has selected observation number 308, then it has selected 258, then it has selected 552 and so on. Right, somewhere it has selected 1, so the first observation is also there. It has selected 2, it has selected 3. So these are the different observations that are going as a part of the training data. Right, so this is the train which 700 numbers are taken. Now if I want to call it as a training data, I will take these subsets from my credit underscore min max. Is it credit underscore min max or is it credit min max? Credit min max. So I will be typically taking credit min max. I'll take a subset of credit min max. Right, I will take the row numbers as the train. I'll not take all the 1000 rows. I'll take only these 700 rows. So that's where I have given the input as train, and I'll take all the columns. So that's where I have left the columns as blank. So the training data is these particular variables. Similarly, I need my testing data as well, which I would be taking as the same credit min max, but I have to take it as something that is those rows which are not there as a part of the selected. So I'll take it as minus train comma blank. So my training data is those 700 rows which are there as a part of the train, and the testing data is those 300 rows which are not there as a part of the train. So that's where I have taken the subset as minus train. So I have broken the data into a training data as well as a testing data. So we have done this in a random manner using the sample function. Important that each data set is a representative subset of the full data, so that's where I should not be biased in the selection of the sample. I will not take the target variable. Anyhow, my credit min max does not contain the target variable at all. So I am not considering the target variable at all. So I have considered only the credit min max, which contains only the explanatory variables, but it does not contain the target variable. So my step 4 is done here. So in my step 5, I am actually initiating my training learning model. Right? So I am training the model now for the data. So for the KNN algorithm, we have already said the training phase is a very quick phase, because there is no model building that is involved in the KNN process. Now, to implement the KNN algorithm, first thing I need to have a package called class. Let me see if I already have a package called class. I'll do a library class. Yes, the package is already there, so that's where I have loaded this package. Then I have to use the KNN implementation for that particular package. We'll see how to give that as an input. So KNN is the name of the formula. This is what we have to give. So let me come there. So the KNN algorithm, it is providing a standard classical implementation of the KNN algorithm. So for each instance in the test data, we have 300 instances in the test data. So for each instance in the test data, the function will identify the k nearest neighbors. So I have to specify how many nearest neighbors need to be identified. So it will identify the k nearest neighbors. Typically we have said the k should be more or less equal to square root of n, where n is the size of your training data. So now my training data is approximately 700. So if I want to take the square root of 700, it is approximately around 26.45. I better go with 27. I generally prefer an odd number rather than even number, so that the tie would be broken quite comfortably. So I will take my k as 27 here. Now, but I don't need to restrict myself to 27. I can try 25, I can try 29, different kinds of numbers. But for each instance in the test data, out of those 300 instances, so this work will be done 300 times separately. The function will identify the k nearest neighbors, 27 nearest neighbors out of that 700. The function will identify the 27 nearest neighbors out of that 700 for each and every instance of this 300. And the nearest neighbors are identified using the Euclidean distance mechanism itself. Now, once those 27 nearest numbers are identified, the classification is basically done through a voting system. So all these, out of these 27 of them, how many of them have gone into the default category? how many of them have gone into the non-default category. So whichever the category is the maximum out of these two, let's say this is 14 and this is 13, then this instance would be classified as default. So that is what we are saying. So there is a voting that is taken among the k nearest neighbors. So and it's assigning the class of the majority. The tie is broken through this particular manner. Here there is no question of tie. But in case when I am taking my k as only 26 and the tie has actually resulted, then the tie is broken at a random manner itself. So the way you have to give your algorithm straightforward, KNN, numeric training data. So let's start the function now. KNN is the name of the function. If you want, let's store this in the model. So let's create a variable called model KNN 27, and this is for min max. Right, probably I'll call it as model underscore min max underscore KNN with 27 as a k value. So this is the name of the model I am giving. Min max is the normalization that I have done, and I have set the k value as 27. So I am giving that as KNN as a formula. The first input I have to give is numeric training data. Okay, training data is nothing but I have stored it under a variable called training data. Right, all of them are numeric and they are all normalized already. Then I need to have numeric testing data. So which is the name of the variable for my testing data is this is where my testing data is there. So this should not include the target variable. So these are the two inputs that I have to give. Class of training data. One more thing that I have to give. The class of the training data. So for the training data's class, I have to refer to my credit underscore new itself, because credit min max and all, they don't contain it. So I will very well take credit underscore new dollar. What is the variable for the class? Let me just go back and look at the variable for class. It is default. Right, credit underscore new does not contain the default. Right, so I have to go even one more step, credit. So I'll take it as credit dollar default. Right, so I can't take credit underscore new, that does not contain the target variable. So I'll take credit dollar default and I will take only the training data. So that's where I'll take those rows which are there as a part of the train. And the number of nearest neighbors that I want, let's say I want 27 nearest neighbors here. So I'm building the model in this way. The model is already built. Right, now model mm underscore 27 is the output of the KNN model, where I have given the training data of the 700 rows, I have given the testing data of the 300 rows, I have taken the class of the 700 rows of data from the credit, and then I have taken 27 to be the size of the k. So there is a factor variable. Now if you simply type model underscore mm underscore 27 to see what this model has typically created, it has finally given me the 300 outcomes. Right, which of them are yes? There are some of them which are coming out as yes, some of them which are coming out as no, which is more like a prediction in terms of the it's a factor vector getting predicted labels for each of the cases in the test data set. For each of the 300 cases in the test data set, it has typically created the result as either yes or no. So it has done the whole process. So sometimes I could directly type in the model, which will give me these kind of values. Sometimes when I want to do a summary of this particular model, I will simply get it as there are 256 no's that this model has predicted and 46 S's have been predicted by the model. So I have to really compare it with the actual. So these are the predicted values based on the learning that the model has typically done, right? These are the predicted values. So if you want, sometimes you can do a structure of the model also to see what all are being retrieved by this model, right? You can look at the structure. The only thing it retrieves is the factor. That's it. It does not retrieve so much of because there is no model formula created. It's just doing one by one. Okay, for the first observation in the test data, which 27 observations in the training data are closest to it. Based on this 27, how many of them are having a class of default and how many of them are having a class of no default. Based on the majority, the first record is assigned a value of S. That's it. No other thing is being stored as a part of this model. We have to be very clear on the process that the KNN algorithm is typically executed for us. Then, the next step for us is evaluate the performance of the model. So I can very well evaluate it through the table itself, right? Table, wherein I take the predicted values. The predicted values are coming out with the model MM27, and I can also take the actual values. The actual values I will take it from credit dollar default, which will contain the minus train data. I'll take the minus train rows out here. So I'll do a table of this. So which will give me, this is the table. So predicted no. So you could see that predicted there are 256 no's. So the breakup is 204 plus 52. And similarly predicted yes, there are 44. The breakup is 24 and 20. So this is how the classification has typically come out. Which means 204 people for whom the model has predicted that they will not default, in actual also they did not default. So the model has done a correct prediction for these 204 people. Similarly, for this 20 people, the model said yes, they will default. In reality also they have actually defaulted. So the model has done a decent prediction here as well. Whereas look at the other numbers, this 52, your model has said they will not default, but in reality they are going to default, which is going to be a pretty heavy expense for you, right? This is going to be a pretty heavy expense. Whereas this one, your model said that they will default, but in reality they have not defaulted. Probably this looks like a more cautious kind of an approach. You are saying that they are going to default, whereas in reality they did not default. So it's like you might not be giving loans to these kind of customers. Whereas these kind of customers, because your model is saying that they are not going to default, they will not default, but in reality they have defaulted, that is going to be a very serious error. So overall, if you are looking at the accuracy of your model, it is nothing but 204 plus 20, 224 out of 300. So the accuracy of the model is around 74.66%, whereas when you are looking at the error rate, it is 76 out of 300. So the model is having almost 25.33% of the overall errors. Some errors are very much expensive compared to the other. Either I can do the simple table or I can very well use the cross table also. So cross table we have already seen earlier. We have to use it from the G models package because it's already installed. I am directly loading the G model and I can very well take the cross table with respect to the same inputs. I'll do the cross table with respect to the same inputs. You may get the same kind of an output but slightly more sophisticated, right? So if you want the t-test also, you can very well see the chi-square test, but this is the kind of a table that is typically coming out. But what I want you to look at is more of an agreement between the two vectors. Look at the true positives So both of them being S's, the true positive, both of them are positives. So your prediction is also positive and the actual is also positive 20. False positive, right? The actual is positive default, but your model has been predicted as no. So this is a false positive which is going to have a very serious consequence. Then false negative, your model has predicted as no and even reality was S. So it's a false negative. So in this case, the seriousness wise, the false positive is much more dangerous compared to a false negative. And then we also have a true negative. This is a true negative. So you look at all these four instances. So we'll have another way of evaluating these four in our later exercises. But you can compute the accuracy of the model based on this. Now what you can very well do is there any other way you can improvise the model? Because for me, if I have to use it for testing purpose, the misclassification should be as much lesser as possible. Here the misclassification is almost 25.33%, which is a very higher number. So I want this misclassification to be as much lesser as possible. Now this is where we talk about the next step. Is there any way I can improve the performance of the model? So I might try out the same thing. Instead of building it on the training on the min-max data, I may want to build it on on the Z transform data. Or that is one way to look at. And even on the min-max, the other thing that I would like to look at is change the values of K and then try evaluating the model. So if I have to change the values of K, instead of 27, let's say I want to make it 25. Right? Let me build the model with 25. Alright. So once I have built the model with 25, I will simply test this model. So these two steps I may have to repeat to see the accuracy. Okay, so right now it is the accuracy is 222 only, and 78 is having error. So 78 out of 300 are having errors, which is almost 26%. So this is also bad. So let me say, instead of 25, just for the sake of doing it, let's say I want to build it with only K as 5. Right, I am trying to build it with K as 5. So now when I am trying this model out, I am testing it with K value as 5. The accuracy is 35 plus 42. 77 is the error part. 77 out of 300. Again still the same. So I want to try out different values of K where my error can come down quite drastically. And whichever is that particular value of K where the error is coming down quite drastically, I could do a kind of a looping out here. So I would like to try out the different values of K, and based on the different values of K, I want to test out for which values I am getting the highest accuracy or the lowest amount of the misclassification rate. Or in some cases, rather than relying on the min-max method, I can also look at the Z-score method. Right, so I will go with the Z-score method now that I have looked at all different possibilities. Otherwise, let me call it as training data 1 so that I'll have a backup of everything. Right, so I'm taking the Z-score And similarly, I can take the Z score for testing data as well. So instead of credit min max, I'll take Z score. I'll call it as testing data 1. Now I can very well build my model. Let's say the 25 model itself. Let me build it. Instead of calling it as model, let me call it as a Z score model. KNN. I'm taking the training data 1 as the input, testing data 1 as the input, credit default train 25. Let me now test the accuracy of this model. The accuracy of this model also is more or less, oh sorry, I cannot take MM25. Let me call it as Z25. The accuracy of this model looks like 208 plus 16. 224 are correct, 76 are errors. So I am going with 76 out of 300. Now in all these cases, if you look at, probably this error, this looks like much better because this classification error, which is a very dangerous error, this number has come down quite drastically to 42 here compared to various other methods. Now even if I increase the same to 27, the same process, if I increase it to 27, which is close to that square root of 700, right, if I increase it to 27 also, I could see that the accuracy of the model is still 77 is the error rate, and this is 57, which is still severe. Now I should try out all these different kinds of possible combinations and see which particular value of k is trying to reduce my overall error rate, so that the system is able to do the learning process more and more effectively there. And based on that, the more and more higher accuracy I am getting, the more and more the lesser and lesser misclassification rate that I am able to generate, that particular value of k I would be using for the futuristic prediction purpose. And at the same time, I would be using different other classification models as well for the same data. I'd be using different other classification models to finally come out with a mechanism of which model is more and more appropriate in terms of doing the classification of this data more and more accurately. But as far as this model is concerned, this is the process that we are adopting, learning from the data, learning the classifications from the data, using it to do the predictions for a new set of data. If the accuracy is much higher on the testing data, then I could have directly implemented it for the production data also quite comfortably. But here, I'm not getting an error rate which is lesser than 25% at all. So I have to see if some other model can do the fitting of the data more and more appropriately. So these are some of the things I wanted to cover as a part of this session. I think all of them we have dealt in much greater depth. So if you have any further queries regarding the same, you can give me a call on this number that I have provided below, or you can send in an email at the email address that I have given below. Thanks a lot for listening to this session. Thank you very much.